let's consider two cavities, two bodies, if you want, and they have a different shape. For example, this is the first body at temperature T, and then we have another body at the same temperature T, and these two are concave bodies, so they are cavities, and radiation can enter from a small hole here, for example, and let's assume that this hole is connected to another small hole in this other cavity. Let's assume that this is cavity number 1 and it has shape number 1, and this has a different shape which I will denote as shape 2. Now, if the two cavities have the same temperature, there should be no flux, right? No flux of energy going from one to the other. Therefore, this means that the energy per volume, and I will denote it as U, will be a function of T. It will not depend on the shape, right? Because even if the shape is different, there should be no flux from the one to the other. So we can consider just a cube, a cubic cavity. I will draw a cube here, and there is an origin of coordinates and three axes, x, y, z. The side of the cube is A, so these are all equal to A, these sides. And we have to consider, since we are considering radiation, we will consider the wave equation del squared phi equal to 1 over c squared del squared phi dt squared, where phi can represent both the electric and the magnetic field. B, magnetic field, and also the electric field E. And they can be also multiplied by a constant if you want. For example, we can consider CE, and therefore the units of this are equal to the units of this, but that's not really important. Now, if we consider the wave equation, I want to solve it, we can find that the modes can be written in this form: sine of kx times x, sine of ky times y, times sine of kz times z, times the sine of omega t. And this is, let's say, the component phi j. It's just one mode, but if you insert this expression into the wave equation, you will find another expression that should be satisfied, which is kx squared plus ky squared plus kz squared equal to omega squared over c squared. Okay, and we have to impose that phi j of 0 y z t is equal to 0, and 0 should also be equal to phi j of x0 zt. So on the sides here, on the surfaces of this cube, the field phi should go to 0, because the field is related to forces. For example, a charge multiplied by the electric field gives us a force, and the velocity times the charge times the magnetic field is also proportional to a force, right? So it makes sense that if there are no forces and there is no dissipated energy due to friction, because we are talking about a black body, so all the energy is absorbed and re-emitted. There is no dissipation of energy. It makes sense that these components here should be 0. So we also have phi j x y 0 t. This one should also be 0. As I said, otherwise there would be forces on the faces of the cube, which would produce dissipation of energy. But what this implies, what these conditions here implies, that kj, and j can be either x, y, or z, times a should be equal to pi n. So this is the only way to make those signs equal to 0 on the faces of the cube. So from here we get kj equal to pi nj over a, where n is an integer. So this equation can also be rewritten like this. It can be written as n1 squared plus n2 squared plus n3 squared. So instead of nx, ny, and nz, I have simply rewritten n1, n2, n3, but that's the same thing. And this is equal to a squared omega squared over pi squared c squared. And since omega is equal to 2 pi times the frequency that I will call nu, this can be written as 4a squared nu squared divided by c squared, which implies that the radius of the sphere, because this is the equation of a sphere, if you take a look at this, where the variables are n1, n2, and 3, the radius of the sphere is just 2a nu over c. Now, let's consider the first octant of a three-dimensional space where the axes are k1, k2, k3, or if you want kx, ky, kz, but that's just the same thing. And here we draw a cube representing the first mode of our electromagnetic wave. So here this point has coordinates 0, pi over a, 0, whereas this one has coordinates pi over a, 0, 0. And this is simply due to this condition that we have found here, where I have set nj equal to 1 for the smallest modes, right? And we have another mode here, 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 and you can see that they make a cube. Then, in this first octant, we also have to consider the volume of the sphere, because k1 squared plus k2 squared plus k3 squared should also satisfy this equation here, right? So we also have to consider the equation for a sphere there, with radius, in this case, omega over c, if we are using the coordinates k1, k2, k3. So the number of modes that are contained in this first octant is given by 1 over 8, because we are in the first octant, so we have to divide by 8 the volume of the sphere, which is 4 over 3 pi, the radius cubed, which is omega over c, so it's omega over c cubed, and then we divide by the volume of this small cube here, which is pi over a cubed, and we also have to multiply by 2, because this kind of drawing can be done for both the electric field and the magnetic field. So we have two kinds of modes, and this calculation gives us 1 over 8 times 8 over 3, then we get 1 over pi squared, we get a cubed, and that's the volume of the cube that we defined here. So I will call it capital V. This volume I will call it capital V, which is just a cubed. And then I have omega cubed over c cubed, like this. Now if we take the differential of n, so we are considering just the modes contained between the frequency omega and the frequency omega plus d omega, this is equal to omega squared over pi squared c cubed d omega times the volume V. Now the infinitesimal energy per unit volume can be written like this: U of t, and this is the energy per unit volume, and we are considering that the temperature is equal to T. This can be written as the energy that I will call rho per unit volume, but also per unit frequency omega. We have to multiply this by d omega because we are considering in this case that this is energy per unit volume but also per unit frequency, and this should also be integrated from minus infinity to plus infinity to eliminate the dependence upon the angular frequency, just the frequency if you want, because U is the energy density per unit volume, but it takes into account the emission or absorption at every frequency. So on the right here we should integrate overall frequencies. And let's consider rho t omega d omega like this. This is also equal, this can be written as the average energy per mode that we have to find times the differential of the number of modes. So the small number of modes between the frequency omega and omega plus d omega. And since this is energy per volume, we also have to divide by the volume of the cavity, that's a cubed, but I will just call it v. And we know that this does not depend on the result does not depend on the shape of the cavity. So that's why we confined ourselves to the simple case of considering just a cubic cavity. So here we can write rho of t omega equal to average energy per mode derivative of n with respect to omega times 1 over v. And so from this expression here, we can find this quantity, and therefore we can write rho of t omega equal to omega squared over pi squared c cubed times the average energy per mode. If instead of the angular frequency we want to use just the frequency nu, and we know that omega is equal to 2 pi nu, we can rewrite rho as a function of nu and t instead of t and omega. So in this case I have changed the order between nu and t, but that's not really important. I could have also written this as rho of omega t. That's not important. Rho of nu and t can be written by replacing here just the expression for omega, which is 2 pi nu, but we have to be careful because the definition should actually be this one. Let me do it here. So we have to multiply this by d nu, and this is equal to rho of omega t d omega. So this is the actual definition that we should consider because we are using definitions that take into account also the differentials. So let me divide this by d nu, and of course here I will have to cancel d nu equal to, instead of rho of omega t, I can simply rewrite the expression above, this one here, but I have to replace omega with 2 pi nu, so I get 4 pi squared nu squared over pi squared c cubed. This will cancel this one. Here I also have to consider average energy per mode, and d omega over d nu, it's simple, it's just 2 pi, so we get 8 pi nu squared over c cubed times average energy per mode. Now we want to rewrite this rho of nu t in a different way because this is energy per volume, but we want to use power per surface. This can be written as energy per volume, and this can also be written as power divided by volume per frequency because frequency is 1 over time, so power over frequency is energy. And here we have power, we can rewrite this as power divided by a surface times a velocity here. And the velocity that we have to consider here is the speed of light. Speed of light because that's the velocity at which light propagates, and we are considering light after all. And this surface that we are going to consider, let me do a sketch below. Let's consider an infinitesimal element of the surface of the cavity, ds. And some light ray can be emitted, for example, in this direction, but they can be emitted in any direction. And if we project ds along the perpendicular plane to the direction of propagation of this light ray, I will call this ds perpendicular. And this direction of the light ray forms an angle phi with the normal to the surface as ds, then this angle is phi here between ds and ds perpendicular. So ds times the cosine of phi is equal to ds perpendicular. But what I wanted to highlight here is that this surface that we want here is actually surface perpendicular, the perpendicular to the light ray. This light ray has a speed that's equal to the speed of light c, and it's describing in a small amount of time, let's say dt, a volume. And the volume is simply given by ds perpendicular times c dt. That's the volume. And here we have a small volume described by that light ray in a small amount of time dt. Consider that we are looking at these surfaces here, for example, ds. I drew a line here, but you have to consider as if you were looking at the surface from the side. Then we also consider this quantity here per unit solid angle. So in the denominator we will have solid angle because this is the power emitted per unit solid angle and per unit surface. And then we also have to multiply this by the total solid angle, 4 pi. So here I could have also put 4 pi, which is the total solid angle. So we have divided this power by 4 pi because we started from energy per volume, which had to be considered emitted in all directions. But in this case, we are just considering this part to be emitted per unit solid angle. That's the difference. And let's put this constant c here. We have c. And now we define this as q sub omega, which defines the power per surface per solid angle. But if we want the power per surface, that I will call q, and this will be power per surface and not surface perpendicular, we have to integrate q omega times the cosine of phi d omega. Why is that? Well, because you see from here that ds perpendicular is equal to ds over cosine phi. So ds perpendicular over cosine phi is equal to ds. And since we have surface perpendicular here in the denominator, and you should consider this as ds perpendicular. So just consider the differential as perpendicular. And here you should consider ds. So if you multiply q omega by cosine phi, q omega times cosine phi is power divided by ds perpendicular times solid angle here in the denominator, solid angle, and you also have to multiply by cosine phi, but you can put cosine phi here. So this will become ds. So we are defining in this case Q, in terms of the actual surface, ds, which is not perpendicular to the light ray. And we have to integrate over d omega if we want to consider Q as emitted in all directions. So not only emitted per unit solid angle, but it will be emitted in all directions. And therefore, we can rewrite this as integral. Now, in general, if we consider a small surface like this, we have a normal n, and we have a light ray, for example, like this, and this is the angle phi. So our z-axis is along the normal, and the d omega can be written as, so here we have q omega cosine phi, we have sine phi, d phi, d theta, and we have to integrate over theta from 0 to 2 pi and over phi from 0 to pi over 2, like that. Then q omega does not depend on phi, so if you carry out this integration you get pi times q omega. So from these results you have q omega equal to q over pi, and remember that q omega can be written also in terms of a rho, because q omega times 4 pi over c is equal to rho. Remember, rho of nu t is equal to q omega, which is also a function of nu and t, 4 pi over c. This is also equal to 4 over c times q of nu t, like this. So q of nu t is equal to c over 4 times rho of nu t, but we have the expression for rho of nu t, and c over 4 rho of nu t, but we have the expression for rho of nu and t, and therefore we can rewrite, if you substitute this as 2 pi nu squared over c squared average energy, like this. Now for the average energy, Planck used his mathematical trick, and instead of considering Maxwell-Boltzmann distribution in the continuous case, he considers it in the discrete case. So light is made of quanta, and you can rewrite this as sum over j, epsilon j, e to the minus epsilon j over k Boltzmann t, and then here we divide by sum over j, e to the minus epsilon j over kt. So 1 over kt is usually called beta, so we can rewrite this as sum over j, epsilon j, e to the minus beta epsilon j, divided by sum over j, e to the minus beta epsilon j. And this can be written as minus the derivative with respect to beta of natural log of the sum over j of e to the minus beta epsilon j, like this, where epsilon j should be written in this form. It is equal to j, which is the integer j, times h, Planck constant, times nu, the frequency. So this was a Planck mathematical trick. It's this one here, thanks to which he hypothesized that energy is discrete and the energy of the photons is proportional to the frequency, nu, of the photon. And he also used, in conjunction with it, since energy is discrete, of course, this formula in the discrete case. Now let's rewrite this sum by using this formula. Let me do it below. We have sum over j, and j is an integer which goes from 0 to infinity. And here we have e to the minus beta h nu to the power j. This is geometric series, and it gives us 1 over 1 minus e to the minus beta h nu. And therefore we get that the average energy can be written as derivative with respect to beta of natural log of 1 minus e to the minus beta h nu. So I have simply put this thing here in the numerator, and I can do that because I have logarithm of 1 over this, but the logarithm of 1 over this is minus the logarithm of the denominator, and therefore the minus sign will cancel this minus sign here. That's just simple mathematics. So if we carry out this derivative, we have that this can be written as e to the minus beta h nu times h nu divided by 1 minus e to the minus beta h nu, and this can be written as h nu divided by e to the beta h nu minus 1, like this. Now if we consider the limit as nu goes to 0 of the average energy per mode, if you consider just this limit, if you calculate this limit, for example, by using the L'Hopital, you get h divided by beta h, which is 1 over beta, which is K Boltzmann times temperature. Whereas if you consider the limit as nu grows larger, it goes to infinity of average epsilon, this is 0. You can see there from the formula. The average energy epsilon is 0 when the frequency is very large, whereas the average energy is K Boltzmann T when the frequency is very small, almost equal to 0. So here we have found this result. Remember the expression for Q of nu T. I'm going to put it here. Q of nu T is equal to 2 pi nu squared over c squared times the average energy, but we have found the average energy here, and that's just h nu divided by e to the h nu divided by kt minus 1. So this can be written as 2 pi h over c squared nu cubed divided by e to the h nu over kt minus 1. And if we want to find q of t, so the power per surface, which is the radiation emitted in all directions at every frequency, we have to integrate from 0 to infinity the formula above. So we get q of nu t, the nu, we have to integrate over the frequency nu. And this is equal to 2 pi h over c squared, integral from 0 to infinity, nu cubed divided by e to the h nu over kt minus 1 d nu, like this. Now if we make a substitution and we set x equal to h nu over kt, we get dx equal to h over kt d nu, and therefore q of t is equal to 2 pi h over c squared times, here we have kt over h cubed times kt over h from the differential, integral from 0 to infinity of x cubed dx divided by e to the x minus 1. So let me reorder those terms. 2 pi over c squared, then we get k to the fourth e to the power 4 divided by h cubed, and then we have the same integral from 0 to infinity x cubed over e to the x minus 1 dx. And this integral can be computed, so let's calculate the integral from 0 to infinity of x cubed divided by e to the x minus 1 dx. is equal to integral from 0 to infinity of x cubed of e to the minus x over 1 minus e to the minus x dx, and this can also be written as integral from 0 to infinity of x cubed summation with index j going from 1 to infinity of e to the minus x to the power j dx, and this is equal to summation j from 1 to infinity of integral from 0 to infinity x cubed e to the minus jx dx. This can be written in this form: summation from j equal to 1 to infinity integral from 0 to infinity d cubed d alpha cubed e to the minus j alpha x times 1 over minus j to the third power dx. And then we set alpha equal to 1. You can check that if you take the derivative with respect to alpha of this term 3 times, you get back this term if you set also alpha equal to 1. That's just simple to do. This can be rewritten now. If you carry out the integration with respect to x, you get summation j from 1 to infinity minus 1 over j to the power 4, and then we have derivative 3 times with respect to alpha of 1 over alpha, right? Because if you consider this integral, it's quite easy to carry out. Then we have this is equal to sum from 1 to infinity over j of 1 over j to the power 4. This is second derivative with respect to alpha squared of 1 over alpha squared. Remember that we also have to set alpha equal to 1 at the end. So here we have to set alpha equal to 1 when we do the calculation. This is equal to sum j going from 1 to infinity 1 over j to the 4 minus 2 over alpha to the third power, and then we set alpha equal to 1 here. And finally, we get that this is equal to 6 times summation with j going from 1 to infinity of 1 over j to the power 4. And now if we manage to calculate this series, we manage to calculate the integral that we started from, this integral here. The way to calculate this series is by using Fourier analysis. We have to consider the function y equal to x squared, and we assume that x is between minus t over 2 and t over 2. So the function is periodic with period t, and we are going to consider this interval, and we are going to expand y in a Fourier series. So we know that we can write this as a0 over 2 plus sum with the index 1 going from 1 to infinity of an times cosine of omega n x, where omega n is 2 pi n over the period t, plus bn times sine of omega n x, and an over 2 can be written as 1 over t integral from minus t halves to t halves of x squared cosine of omega n x dx. And since this function inside the integral, the integrand is symmetric, we can start at x equal to 0, and we simply put a factor of 2 here. Something similar for bn. bn over 2 is equal to 1 over t integral from minus t halves to t halves x squared, but in this case we have sine of omega n x dx. You can see that this function here is odd, so this integral will give us 0. But let's calculate an. So this one here can also be written as 2 divided by t omega n integral from 0 to t over 2 x squared differential of sine omega n x, which is equal to, so we can integrate by parts, 2 over t omega n times t squared over 4 sine of omega n t over 2 minus 2. Then we have integral from 0 to t halves x sine of omega n x dx, like this. This integral here can also be calculated. It's easy to do. We have integral from 0 to t over 2 x sine of omega n x dx. We can integrate by parts. We can rewrite it as minus 1 over omega n integral from 0 to t over 2 x differential of cosine omega n x, and this is equal to minus 1 over omega n times t halves cosine of omega n t over 2 minus integral from 0 to t halves cosine of omega n x dx, and therefore we get that this is equal to minus t over 2 omega n cosine of omega n t over 2 plus 1 over omega n squared sine of omega n t over 2, like this. So if we put these results together, we have a n over 2 equal to 2 over t omega n times t squared over 4 sine omega n t halves plus t over omega n cosine of omega n t over 2 minus 2 over omega n squared sine of omega n t over 2, and this is equal to 1 over pi n t squared over 4 sine of pi n. Now we have replaced the definition for omega n, which is 2 pi n over t. So we have sine pi n here, and this will be 0 plus t squared over 2 pi n cosine of pi n plus 0. This last term will give us 0, and this is equal to t squared over 2 pi squared n squared times minus 1 to the power n. And finally, we also have to find a0 over 2. a0 over 2 is equal to integral from minus t halves to t halves of x squared dx, and we also have to multiply by 1 over t. This is equal to 2 integral from 0 to t halves x squared dx over t, and this gives us 2 over 3t, and then here we have t cubed over 8, so this is equal to t squared over 12. So f of x can be written as t squared over 12 plus summation from 1 to infinity of t squared minus 1 to the power n divided by 2 pi squared n squared times 2 cosine of omega n x. If we use Parseval's theorem, it's easy to find that integral of f of x squared dx from minus t over 2 to t over 2 and we divide by t. This is equal to a0 squared over 4 plus sum from 1 to infinity of an squared over 2. Remember that bn is equal to 0, and this is equal to 2 over t integral from 0 to t halves of x to the power 4 dx, which is equal to 2 over 5t, t to the power 5 over 2 to the power 5, and this is t to the power 4 over 80. If you insert the expression for a0 and an into this formula, you will get something like this: t to the power 4 over, now a0 was equal to, remember, a0 over 2 was t squared over 12, so here we get 4 times 36, and this is 144. Then we get plus, if you do the same for an squared, you have t4 over 2 pi to the fourth sum from 1 to infinity of 1 over n to the power 4. And this should be equal to t4 over 80. From this expression, if you solve for this series here, you find summation with n going from 1 to infinity of 1 over n to the power 4 equal to pi to the fourth divided by 90. And remember that we wanted to find this result because we also wanted to find the integral from 0 to infinity of x cubed over e to the x minus 1 dx. And now you find that this is equal to 6 pi to the fourth divided by 90, which is pi to the 4 divided by 15. Because the result of the integral was given by 6 times the series. You see it from here. And then we can also substitute back in our formulas, because this integral here appeared in the formula for q of t. Q of t is equal to 2 pi over c squared k to the fourth divided by h cubed pi to the fourth divided by 15 t to the fourth. And this is equal to sigma 0 times t to the fourth, where sigma 0 is the Stefan-Boltzmann constant, which is given by these constants put together here. So sigma 0 is pi to the fifth power k to the fourth power times 2 divided by c squared h cubed 15 here in the denominator, which is approximately equal to 5.7 times 10 to the minus 8 watts per Kelvin to the fourth per meter squared. And Boltzmann constant is approximately 1.38 times 10 to the minus 23 joules per Kelvin. H is equal to 6.6 times 10 to the minus 34 joules times seconds. And of course, the speed of light is 3 times 10 to the 8 meters per second.